Kaydı başlattım. Share the slides. Okay. We are at the chapter 10, which is on graphs. In this chapter, we are going to talk about graph structure. Actually, you all know what a graph is, and several graph terminology is familiar with you, but we are gonna talk about them anyway in a little bit more detail. And then we are gonna define the graph as an abstract data type. We are gonna talk about implementation of this graph abstract data type, and then we are gonna talk about several algorithms. First of all, traversal algorithms, then weighted graph algorithms like minimum spanning tree, shortest path algorithms, etc. We are going to talk about these different algorithms in this chapter. Graph is a generalization of tree structure. In tree structure, as you all know, there is no back edge, a limited data structure, but in graph we generalize this, and there are lots of notions like road maps, airline routes, course breakers, and so can be defined as graphs. And by using these representations, we can solve several different problems on these structures, like finding a route from ST to another using the airlines, or we can find the order of the courses that fulfills the prerequisite requirements, or we can find the shortest path from one place to another, etc. So several problems can be solved by using graphs. First of all, we are going to talk about terminology, what a graph is and what kind of terms we use to describe graphs. Okay, graph contains two sets. Actually, we usually represent graph as two sets. One is vertex set, the other one is edge set. So a graph is a tuple with two sets. First set is the set of vertices. The second set is set of edges. We call vertices as nodes. We are going to use these two terms interchangeably. And edges are relations between pairs of vertices. So if two vertex A and B, we define a relation, and we are going to call this as a edge. Okay. So edges represent relations or connections between vertices. So in this graph, both these sets can be empty. For example, if the vertex set is empty, there is no vertices, so there is no relations. Edge set should be empty as well, so the graph is an empty graph. But even if the vertex set is not empty, we may have an empty edge set. In that case, all the vertices have no relation between them. So we can have such graphs as well. Even sometimes it is not so useful, but still we can have that kind of graphs. We restrict our discussion on simple graphs where between two vertices, vertex A and B, there can only be one edge or not. We cannot have more than one edges in simple graph. So we are gonna concentrate on simple graphs where there is at most one edge between any two vertices, A and B. Okay. As you see, a graph can be represented with two sets. Vertex set, this is the vertex set. In this vertex set, we have 5 vertices, and we have an edge set. In edge set, we have again tuple of vertices. So this means there is a relation between A and B. This means there is a relation between A and D and C and E and D and E. So these are the edges in edge set. This is one representation of graph. Mathematically, we can represent a graph with two sets, as in here, but we can also represent graphs visually. In visual representation of graphs, we take each vertex and put a circle around it. So vertices are represented by small circles. These are vertices. Of course, each vertex has a name, so these circles are labeled. So each vertex is represented by labeled circle, and edge between vertices are represented by lines joining the vertices. So this edge is represented here, this edge is represented here, etc. Actually, this is a representation of the same graph. These are two equivalent representation, the equivalent graphs. We can draw the same graph as follows. For example, D here, A here, A, B here. Oh, not B, E. And C here, and B here. Right? This is the same graph since it has the same vertices and same edges. As you see, this edge is here, this edge is here, this edge is here, and this edge is here. So all the edges are represented and nothing more. So this true representation, or actually two representations, are equivalent. So in graphical representation, visual representation, the places, positions of the vertices are not important. You can place the vertices anywhere you'd like, since the graph is represented by two sets, and here in this representation there is no places for the vertices, position for the vertices, and so we can place or position the vertices anywhere in the surface, and we can draw the edges as lines and can have the visual representation. So different visual representations are possible for the same graph. Okay, we usually represent edges by two vertices. So an edge could be x, y. X is a vertex and y is a vertex. So this edge represents the connection between these two vertices. We can also draw it like this, right? So there is a connection relation between x and y, and there is a connection from x to y or y to x in this case. As I said, this is a mathematical representation of a graph where this is a vertex set and this is the edge set. We have 7 vertices and several edges in that case. Physical layout and positions of the vertices is not important in this visual representation. So you can place the vertices anywhere and still the graph is same. So these true graphs are equivalent graphs without any difference. As you see, there is an edge between 4 and 5. There is an edge between 4 and 5, and all the edges are same, even with this representation. So all these representations are equivalent. Okay, gives same meaning. In graphs, the edges can be directed or undirected, and all the edges should be directed or undirected. If a graph has only directed edges, we call that graph to be directed graph. And if all the edges are undirected, the graph is undirected graph. Here in this graph, there is no order between these two vertices. As you say, this is represented as a set. In a set, there is no order between the elements, right? In a set, 4, 3, and 3, 4 are equivalent equivalent sets, the same set. So there is no difference between, there is no order between the vertices in this representation. So the relation between 4 and 3 is both ways. So 3 is related with 4 and 4 is related with 3, or there is a connection between from 4 to 3, and there is a connection between 3 to 4. So there is no direction in this case, but sometimes we may need directed edges. Then we have directed edge. The edge between A and D is represented as a tuple, not as a set. In a tuple, there is an order. First vertex is D, and second vertex is A, which means there is a relation from D to A, or there is a connection from D to A, but there is no connection, as you see, there is no connection from A to D. And we represent that connections visually by using arrows in the lines, right? The edges of the graph is directed if the existence of an edge from A to B doesn't necessarily guarantee that there is a relation in both ways. There is no relation from B to A sometimes, but here, as you see, there is a relation from A to B, and there is a relation from B to A. That's also possible in directed graphs, but we have two different edges in that case, and this is still simple graph since these two edges are different, not like two edges between 4 and 5 here, since this edge means there is a relation from 4 to 5, and this edge say the same thing. There is a relation from 4 to 5. So in simple graph, we do not allow such two edges in undirected graphs, but in directed graphs, we may have two edges in different direction between the two vertices. If the edges are directed, as I said, the edges are represented as tuples, not as set here. For example, for this graph, the edge set is something like A to B, B to A, D to A, E to D, etc. What's left? There are a couple of lefts. You can complete the set easily. So edges are represented as tuple, not as set, as you see. This kind of graph is called directed graph or digraph. If the edges are undirected, we call the graph as undirected graph. This is an undirected graph. Usually when we say graph, it is undirected. We do not call the graph undirected usually. If you say just a graph, it is undirected. If it is directed, we use directed as an we call them directed graph. Or digraph, as I said. So directed edges are like one-way streets, so you can travel from D to A, but not A to D. As you see, directed edges can be represented by arrows, and it is represented as tuples, not sets. Okay. Sometimes we need some value associated with each edge. We call this value as weight usually. So we may have weights on the edges, and if we have such a graph, we call that graph as weighted graph. So this graph is a weighted graph since each edge has a weight, and this graph is undirected graph since edges are undirected. Okay. So we can define paths on this graphs. Any graph we can define paths even for directed graphs. A path is a sequence of vertices. For example, Cleveland, Toledo, Detroit, Ann Arbor is a vertex list, right? Vertex sequence, and it represents a path: Cleveland, Toledo, Toledo, Detroit, Detroit to Ann Arbor, right? So we can we can have a sequence of vertices, and we call it a path. And in this path, we call Toledo is adjacent to Cleveland, Detroit is adjacent to Toledo, and Ann Arbor is adjacent to Detroit. So there should be an edge between Cleveland to Toledo. So Toledo should be adjacent to Cleveland, and Detroit should be adjacent to Toledo, and Ann Arbor should be adjacent to Detroit. A vertex is adjacent to another vertex if there is an edge from that to other vertex. So we call Columbus is adjacent to Pittsburgh. Since it is undirected edge, Pittsburgh is adjacent to Columbus as well. So Philadelphia is adjacent to Pittsburgh, and Pittsburgh is adjacent to Philadelphia, since this graph is undirected graph. But if the graph is directed, A is adjacent to D, so we can go from D to A, but D is not adjacent to A. So D is cannot be reached from A directly, but A can be reached from D directly, right? A direct edge from D to A, so A is adjacent to D. But in undirected graphs, Indianapolis is adjacent to Columbus, and Columbus is adjacent to Indianapolis, since it is undirected, right? As I said, path is a sequence of vertices. So each successive elements in this sequence, for example, between this to this, there should be this vertex X should be adjacent to this vertex Y, right? And it has to be that kind of relation, adjacency relation, should be available between all pairs in this sequence, right? For example, we can have a path from Philadelphia to Chicago. Philadelphia, Pittsburgh, Columbus, Indianapolis, Chicago is a path. And as you see, Pittsburgh is adjacent to Philadelphia, and Columbus is adjacent to Pittsburgh, etc. on this path. A path is called simple path if there is no repeated vertex in this vertex sequence. If all the vertices are distinct, then this is a simple path. Okay, there is no cycle in this path, but this path is simple. But this path, Philadelphia, Pittsburgh, Columbus, Indianapolis, Chicago, Fort Wayne, and Indianapolis, again, is not simple path, since Indianapolis appears twice in this path. So this is not a simple path. It contains a cycle. Here, as you see, there is a cycle. Actually, a cycle is a sequence of vertices, but in cycle, the starting vertex and ending vertex are same. So we start with Columbus. The path goes to Toledo, Cleveland, Pittsburgh, and come back to Columbus again. This is called a cycle. This cycle is simple since no other vertex except the first and last repeats themselves. So it is a simple cycle. First and last are same, but no other vertex repeats in this cycle. So it's a simple cycle. Okay. In undirected graphs, the cycle must contain at least 3 distinct vertices. For example, Indianapolis, Chicago, Indianapolis is not a cycle actually. Indianapolis, Chicago, Fort Wayne, Indianapolis can be considered as a cycle. Okay, in undirected graphs, a cycle must have at least 3 vertices. But in directed graphs, for example here, A, B, A is considered as a cycle as well. From A to B, B to A. We call this as a cycle since we traverse distinct edges from A to B and B to A in this graph. Okay, we can define paths and cycles in graphs. Also, we call a graph to be connected if we can find a path from any vertex to the other vertex. From Fort Wayne to Pittsburgh, there is a path, right? So for any 2 vertices, we can find a path. So this graph is connected. This graph is connected as well for any 2 vertices. For example, between 5 and 7, there is a path, as you see, and you can find a path between any 2 vertices. This graph is connected as well. But this graph is not connected since there is no path from 5 to 7. It is not possible to go start from 5 to reach 7 in this graph, right? So this graph is not connected. If a graph is not connected, it contains connected components. This is one of the connected components. And this is another connected component. Connected component is a subgraph which contains a subset of vertices and edges, and it is connected. As you see, we have 2 connected components in this graph. It still consists of connected components. There are 2 connected components. 4 and 5 forms a connected component, and 6, 7, 8, 9 is another connected component. Okay, we can find connected components in a graph that is not connected. Okay, this connected component can have only 1 vertex as well. For example, in this graph is not connected, and it has 2 connected components. One just contains 4, another one contains 4 vertices, right? We may have 5 here as well. So in that case, we may have 3 connected components, right? One is this one, the second one, and third one. Okay. So we can define paths, cycles, and a graph can be connected, unconnected, directed, undirected, etc. Weighted, not weighted. there are different types of graphs, and we have to know the type from its name, right? There is a relation between graphs and trees, and as I said, graphs are a generalization of the trees. Actually, we can consider tree as a special graph, special case of graph. In a tree, the graph should be connected and shouldn't contain any cycle. So this is not a tree since it is not connected and contains a cycle. It doesn't satisfy neither of these conditions. But this graph is connected, but still it contains a cycle, so it is not a tree. But if I remove one of these edges, then the graph is a tree. But the trees that we have seen so far are rooted trees, and we draw like this, right? For example. Actually, if I write something like 4, 5, 6, 7, 8, and 9, these two graphs are same. So these are two trees, two same trees. Only here we specified a root. So the trees that we have seen so far are rooted trees, where a vertex is specified as a root. So in this tree, we can specify any vertex as a root. For example, if we specify 9 as a root, then the tree would be something like this, right? 6 and 3 vertices connected to 6, 4, 7, and 8, and 5 here, right? All these trees are same trees. This tree is not rooted. This tree has root 9. This tree has root 4. And all of them are same tree as far as the graphs is concerned. As a graph, they are same. But in trees, as I said, we may specify the root as well, and it may change the graph a little bit. For example, here, this is a tree, and this is the same tree with specified designated root of D, right? But they are the same tree, okay? When you consider these two as a graph, they are the same graph. Okay, we can talk about several different applications of graphs. Actually, in your project, you are asked to use graph in your application as well. So you have to find an application of the graph in your project somehow. Graphs can be used in different places. For example, we can determine if a vertex, if a graph is connected or not. If this vertex is network of computers, then we can check whether the network is connected, means any two computers can talk to each other. Okay. Or the graph may represent the course prerequisites, and we may try to find a sequence of courses that we are going to take, which satisfies these prerequisites. So we may try to find in what order that the courses should be taken to satisfy these prerequisites can be an application. Also, we may represent the roads in a city as a graph, and we may find the shortest route from a place to another in that graph. Shortest can mean several different things. For example, if the vertices are the junctions of the roads and the edge between two junctions is a direct road between these two junctions, and if we put some weight for the length of this road, then we can find the shortest length route from some junction to another junction, or some place in an edge to another place in an edge, right? Okay. This is another application that we can use with graphs. Okay, now we have introduced the terminology about graphs. We come to the point to define the graphs as an abstract data type. We are going to define the graph as an abstract data type, and we are going to talk about implementations of two different implementations of this graph abstract data type as in following. So Java doesn't have any abstract data type for graphs. It doesn't define a graph interface or implementations of the graph. So in this book, there is a graph definition, graph interface definition. You can define your own graphs as well as your needs. But for our graph, we need these operations to be supported by the graph abstract data type. Remember, abstract data types are a list of operations. So we have to be able to create a graph with specific number of vertices. We have to be able to iterate through all the vertices in the graph. And another iterator to iterate through the vertices adjacent to a node, to a vertex. So we have a node A, and we would like to traverse the vertices adjacent to A. And we may need to determine whether there is an edge between A to B. If there is an edge between two vertices. And we may try to find the weight between these two vertices. Or we may want to insert an edge into a graph. So this graph we created is it has just vertices. So for example, we may have 5 vertices in the graph when we create it, but there's no edges. Then by this operation, we may add edges in our graph. Okay. Then by using this operation, we can query whether an edge is available or not. By using this operation, we can query the weight of an edge. Or by using this operation, we can traverse through the vertices, iterate through the vertices, or by using this operation, we can take this vertex and iterate through all the adjacent vertices of this vertex. 1, 2, 3. Actually, we should iterate between these 3 vertices. Okay, these are the operations. Of course, when you add more operations, you modify the graph abstract data type, and you can define your own abstract data type and implement it. But for the time being, in the book, this abstract data type is defined, and it is defined as an interface. This is the interface for this abstract data type. So there is no creation method, since this is a constructor. Interfaces doesn't include any constructor. But for example, we have a edge iterator method to iterate through the adjacent vertices to this source. So that is 5, right? No, not 5, 3, right? 3. And this is get edge. It returns an edge. Of course, the weight is part of the edge. So it is 5. And this function, this method returns whether edge is available or not. It is 4. This inserts an edge. That is 6. But there is no method for true or 1, as you see. There are 2 extra methods, is directed and getNumV, but these are 2 getters defined for the graph to check whether the graph is directed or not, and to get the number of vertices in the graph. Actually, these 2 operations, for these 2 operations, the first one is constructor, so it is not defined in the interface. And the second operation will be performed going through the vertices by using this value. So if this value is 5, the number of vertices are 5, then the IDs of the vertices are from 0 to 4. So we can use these values to as vertices, as source and destination. So to be able to traverse to iterate through the vertices, we have to iterate through from 0 to number of vertices minus 1, right? So there is no special method for this, but this is implicitly available. You can always iterate through vertex IDs starting from 0 to number of vertices minus 1, right? Okay, so the vertices are represented by integers. As you see here, when we say source vertex, it's an integer. Destination vertex is an integer. Similarly, here or here or here, the The vertices are represented by integers here from 0 to v, but not including v. This is the number of vertices. We usually call it n. The number of vertices is, we are going to use n for number of vertices. And for number of edges, we are going to use m. Okay. So the vertex indices are from 0 to n minus 1, actually. Okay. So we can traverse, iterate through these integers to iterate through vertices. Okay. For the edges, we are gonna define a class called edge, which will contain the source vertex, destination vertex, and weight as data fields. So as you see here, this getEdge method returns an edge, returns a object of type edge. Edge should be defined. It includes 3 data fields, as I said. For example, to be able to insert an edge, we should provide an object of type edge to insert method. Also, iterator here, edge iterator is of type iterator of edge. Okay. So we are going to define this edge class, which will have at least 3 data fields. Weight is the weight of the edge. If it is not specified, the default value of 1 will be used. And we will consider edges are directed. So edge from source vertex to destination vertex. So destination vertex is adjacent to the source vertex only, not vice versa. You can represent undirected edges by putting 2 edges from A to B and B to A. Okay. So we can still represent undirected graphs, but in that case, as I said, you have to put 2 edges for 1 undirected edge. So this is the class for edges. As you see, we have integer destination, integer source, and double weight as data fields. Of course, there should be a constructor for the edge specifying the source and destination, and another one for specifying the weight as well. And here we have getters for the 3 data fields. Also, as you see, hash code and equals are redefined or written here. They have to be redefined together. If you should redefine equals, you should redefine hash code as well, as we have covered previously. So both are overridden here. So this method will compare 2 edges, whether they are equal or not, and use source and destination values to check whether 2 edges are equal or not. The weight doesn't matter for equivalence. And hash code, of course, shouldn't use weight as in its calculation. It should depend on only source and destination. Since if two edges are equal, their hash codes should be equal as well. Or the hash codes are equal, the objects should be equal, right? So we have to redefine both together. And there is a toString method to get the string representation of an edge. Okay, this is the edge class that we are going to use. So now we defined a graph interface. Now we are going to talk about how to implement this graph interface. Let's have a break before going over this implementation details. 10 minutes break, okay? We are going to continue after the break.